Hey everyone, so this video is going to be about forces. So to give a very simple definition of what a force is a push or a pull on an object. Now, to give an example of a force that you all are probably familiar with in your day-to-day lives, let's say we have a box and a person over here pushing this box to the right. The way we would describe this is the person is exerting a force on the box to the right. And my description of the force brings up a very important characteristic of forces, namely that forces are vectors. So just like velocity and just like acceleration from kinematics, forces have a magnitude and a direction. So the magnitude tells us the strength of the force so it's like some number and then the unit newtons, and that's simply abbreviated with a capital N. The direction is usually given as an angle. So let's say you have some force this way and you have the horizontal like that, and this angle theta can give you the direction of that force. A very important tool whenever you encounter any problems related to forces are free body diagrams. Body diagrams. And what these are a very, very simple sketch of the various forces acting on any given body. And it just helps us visualize the problem. So let's say we have another box. So we have one force to the right. The way we would draw that is just an arrow. Start from the box, move out to the right, and you have a little arrow, and label that F1. Let's say we have another one to the left, out to the left, and F2. The relative lengths of these arrows tell us the relative strengths. So in this case, F1 is stronger than F2. And it's often useful whenever dealing with forces to include the direction of the acceleration. So sometimes you might see somebody and just have a little arrow right here signifying which direction the body is accelerating in. So whenever we're talking about forces, it's very important to have a good understanding of Newton's 3 laws, because they tell us a lot about forces and how objects behave when forces are exerted on them. So Newton's first law says that an object in motion stays in motion, an object at rest stays at rest, unless the object is acted upon by a non-zero net force. So in a slightly more mathematical way, what the law is trying to say is if an object is moving at some velocity, then it'll stay moving at that velocity until a non-zero net force acts on it. And that velocity can be just zero. That means the object is at rest, or it could be 10 miles per hour to 10 miles per hour north, and that could be the velocity. And it'll stay moving at that speed in that direction until a non-zero net force acts on it. And to illustrate what we mean when we say non-zero net force, let's say we have a little tennis ball. Let's say we have two forces on this tennis ball, one to the right, F1, one to the left, F2. Let's say F1 is equal to negative F2. So their magnitudes are the same, but the directions are opposite. So to find the net force on this, we would just sum up. So this like sigma F to show the sum of the forces. That's F1 plus F2, and that's just 0. So in this case, the net force is 0. So the object will continue to move in whatever manner it was initially moving in. However, if we add a third force here, F3, then we have a non-zero net force, and then the object will begin to accelerate and its velocity will change. So this tendency of objects to either stay in motion at a constant velocity or stay at rest is called inertia. And so that's why Newton's first law is often referred to as the inertial law. Now, a very important thing to note when it comes to Newton's first law is the idea of inertial reference frames. So you may remember from kinematics, position has to be defined relative to some origin. So let's say, let's have a good old coordinate axes, your x-axis and your y-axis. And let's say we have another tennis ball right over here. Well, this origin right here needs to be either at rest or moving at a constant velocity for Newton's first law to be true. If the origin by which we define motion is accelerating itself, then Newton's first law is not true. It won't hold true in that reference frame. It's always important to ensure that whatever reference frame you're using is not accelerating. So moving on, we have Newton's second law. So Newton's second law tells us that force is equal to mass times acceleration. And to put that in more mathematical notation, so the sum of the forces, that's a poorly drawn sigma. Sum of the forces is on an object is equal to its mass times its acceleration, and both acceleration and the net force are vectors. So a couple of things we notice right off the bat. The direction of the net force is the same as the direction of the acceleration. And it also tells us something about the units. So earlier we mentioned that forces are measured in newtons. And to find out what newtons are in SI base units, we can look at mass and acceleration. So mass is given in kilograms and acceleration is given in meters per second squared. So newtons are equivalent to kilogram meters per second squared. So let's move this here and shrink that down a bit. Oops. Okay. All right. So let's just work through a couple of simple examples of Newton's second law in action. Let's say we have, a football right here. And let's say that this football is experiencing a force like this in this direction. That's F1. Let's say F1 is equal to 2 newtons. And let's say it's the football's mass is equal to 4 kilograms. We can very quickly use F equals ma to find the acceleration. So a is equal to F over m. So that's equal to 0.5 meters per second squared. And that's just a very, very basic example. And we can look at a slightly more complicated example that might show up, which involves the vector nature, of forces. So let's say we have another football, and it is experiencing is force 1, and also another force, this F2. Now let's say that F1 is equal to 3 newtons. Let's say F2 is equal to 4 newtons. And once again, the mass, or how about the mass is 5 kilograms this time. So, or actually, let's make the mass 10 kilograms. Okay. So first thing we want to find out is what is the net force. And so because forces are vectors, we can't just do 3 plus 4. We have to take into their direction into account. And so we line them up like this. So here we have F1, here we have F2, and here we have the net force. So from since we know that this is a right angle because F1 is to the right and F2 is going downwards, we know that the net force is equal to the square root of F1 squared plus F2 squared, and that's just from Pythagorean's theorem. So we plug in our numbers and we get the net force is equal to 5 newtons. And in order to find the direction of the net force, we can try to find this angle theta right here. And we can use some basic trigonometry to help us find the angle. So we know from the definition of the sine function that sine theta, in this case, would be F2 over the net force. And that would be 4/5. So theta is equal to sine inverse of 4/5, and we plugged it into our calculator and we get that theta is approximately 53.1 degrees. Sweet. Now that we know the magnitude and direction of the net force, we can move on to acceleration. We already know what the direction of the acceleration is because it's the same direction as the net force, so it would be 53.1 degrees below the horizontal, the positive x-axis, so to say. As for the magnitude of the acceleration, we can plug it into F equals ma. So that's the net force. So we have 5 is equal to 10 times the acceleration. The acceleration turns out to be, once again, 0.5 meters per second squared. Sweet. And another important thing to remember when talking about Newton's second law is that it helps us find out what the force of gravity is. So you may recall from kinematics that all objects close to the Earth fall due to gravity at the same acceleration. So with an acceleration is equal to g, and you may remember that g is equal to 9.8 meters per second squared. So now if we want to find out what the force from gravity is, we can use Newton's second law. We have the force of gravity is equal to an object's mass times its acceleration. And since a is just g, we have force is m times g. So if we had, some ball right here with a mass of 10 kilograms, the force of gravity on it would just be mg, and that would be 98 newtons. Sweet. And finally, moving on to Newton's third law. So Newton's third law says that an object exerting a force on another object experiences an equal and opposite reactive force. So to go back to our very, very first example where we had the box and the person next to the box pushing it, the person pushed the box to the right. And Newton's third law tells us that the box will also push the person to the left with an equal and opposite reactive force. So if we were to draw a free body diagram for both of these objects, we would have our box here and a force to the right. This is the force from the person. And if we have our person here, they experience an equal force but opposite in direction to the left. That would be the force from the box, where force from the box is equal to negative the force from the person. So their magnitude or their strength is the same, but their direction is flipped. Now, a common misconception that can arise is that, hey, what if every force has an equal and opposite pair, why don't they just add up and cancel out, and why do things accelerate at all? But it's important to remember that the third law pairs act on different objects. So in this case, one force acted on the box, whereas the other force in the pair acted on the person. So we can't simply just add them up and cancel them out. All right, so let's move this off to the side here. Now, a very important example of third law pairs is normal force. A normal force is the force that a surface exerts on any object resting on the surface in order to make sure that the object doesn't just fall straight through the surface. So if we have a floor right here and then a little box resting on the floor, the box pushes down on the floor with some force of gravity, Fg, and the third law pair to this force of gravity is the normal force, which goes straight up perpendicular to the floor, and this is exerted on the box so that the box doesn't just fall through the floor. And so if you were to draw a free body diagram of the box itself, we would have the box experiences a gravity, that's Fg, and it also experiences a normal force from the floor, which is perpendicular to the floor. And this nature of the normal force being perpendicular is why we call it the normal force, because normal is a synonym for perpendicular. And so if instead of a flat horizontal floor, if we had an inclined plane, then the normal force would be pointed perpendicular to the inclined plane. And notice that in this scenario, the normal force right here is not equal to the force of gravity, as it was in this scenario. In this scenario, the normal force is equal and opposite to the entire force of gravity. Whereas over here, gravity goes downwards. It's not entirely, all of the object's gravitational push is not pushing onto the inclined plane. So the normal force is equal only to the component of the gravitational force that is pushing into the inclined plane. And so, expanding on the idea of the direction of the normal force, if you had a half pipe and someone's skating down the half pipe when they're right here, the normal force points like this, perpendicular. When you're over here, normal force points upwards, also perpendicular. So it can change based on the shape of whatever surface you're on. So to tie all of these concepts together, let's work through an example that requires us to use everything that we've learned so far to solve a problem. So let's say we have an inclined plane, something like that, which makes an angle theta to the horizontal. Let's say theta is equal to 30 degrees. We have a box with mass equal to 10 kilograms. And we want to find out what the acceleration of this box is as it falls down as it slides down the inclined plane. So first, let's draw a good old free body diagram for our box. A box here. We have the force of gravity pointing downwards, and we have the normal force perpendicular to the inclined plane. And so first thing we want to do is we want to find out what the sum of these forces is. And we know the force of gravity is just mass times g. And we know that the normal force is the third law pair for the component of the force of gravity that goes into the plane. So what we need to do is we need to find out what component of of the force of gravity goes into the plane. So we can split up the force of gravity vector into the sum of two vectors. So this is perpendicular into the plane, and this vector is parallel to the inclined plane. And we want to find out what the magnitude of this guy is in order to find out what the magnitude of the normal force is. So we can try to find out we in order to find out what this perpendicular component is, we need to know one of these angles right here. You know that this is a 90-degree angle because these two are perpendicular. These two are perpendicular, so we know that it's a 90-degree angle, but we need to know one more angle. So we can use some handy-dandy geometry to help us figure that out. So let's redraw our inclined plane. So this right here is theta, and we can draw a vector here that's perpendicular going into the plane. We can draw a dotted horizontal line to help us out. Let's extend that out. Sweet. So let's try to figure out what this angle right here is. So we know that this and this are parallel because they're both horizontal. Since this intersects both of them from geometry, we know that this right here, this right here, that is theta. We know that this angle is 90 degrees because this vector is perpendicular to the plane. So we know that theta plus 90 plus, let's call this angle here, let's just call it x. So 90 plus x is equal to 180 because this whole thing is a straight line, so that's 180 degrees. And we solve for x, and we get theta is equal to 90 minus x. Since theta is equal to 30, x is equal to 60 degrees. So now we need to figure out which one of these angles is x and which one is theta. So we know, guys, that we can draw a little dotted line here to help us out. So we know that the angle, so we know this is x, and we know this is theta because that's 90 minus x. So the angle between the perpendicular component and the vertical is theta. Therefore, this is theta and this is x. So now we can use trig to help us find the perpendicular component. So from trig, you know, the cosine theta is equal to f perpendicular over fg. So f perpendicular equals mg cosine theta, because remember the force of gravity is just mg. And therefore, the magnitude of the normal force is also equal to mg cosine theta. Or let's make this one negative because it's going into the plane, and the normal force positive because it's coming out of the plane. And the parallel component, also from trig, we get that it's equal to the force of gravity times sine theta, and that's equal to mg sine theta. Sweet. So now we just have to add all of these up to find the net force. So that's quickly drawn. There we go. The net force is equal to mg cosine theta minus mg cosine theta plus mg sine theta. And that's just equal to mg sine theta. And the acceleration is equal to the net force over the mass. That's from Newton's second law. And that's equal to mg sine theta over m. Both of the m's cancel out, and we get the acceleration is equal to g sine theta. And theta is 30, so sine theta is 1/2, and g is 9.8. So the acceleration is 4.9 meters per second squared going down the inclined plane. And so that's our answer right there. Sweet. Thank you for watching.